Welcome to this quiet journey beneath the stars. Perhaps you've been searching for a moment of peace after a busy day, or maybe you simply enjoy drifting off while contemplating the wonders of our world. Either way, tonight's exploration is especially for you, a gentle voyage across and within our home planet. As you settle in, feel your body growing heavier against the bed. There's nothing to do now but rest and listen. Tonight, we aren't merely observing Earth. We're traveling through its ancient stories, its hidden depths, and its quiet mysteries. We're exploring a world that has been turning steadily for over 4 billion years, a living sphere of rock and water, wrapped in a thin veil of atmosphere. Beneath the familiar surface lies a realm of extraordinary complexity. Continents that drift like slow dancers across a marble floor. Mountains pushed upward by forces so gradual yet so persistent they reshape entire coastlines. Oceans that hide landscapes as varied and mysterious as any found on land. And deep within, a molten heart that beats with primordial heat, driving the great engines of our planet's evolution. You'll hear about ancient stones that remember times when the air was unbreathable, when life existed only as microscopic whispers in shallow seas. You'll drift through forests that communicate through invisible networks, mountains that were once seabeds, and caves adorned with crystal gardens that have grown in darkness for thousands of years. Some of what you hear tonight may surprise you, or at the very least, spark some quiet curiosity as you drift towards sleep. And just before we begin our journey, remember that this planet, this intricate sphere of wonder, is not merely something we live on, but something we live within. We are as much a part of Earth as the oceans and mountains, the forests and deserts, woven into its story through every breath and heartbeat. Now, let's begin. Earth's core is hotter than the surface of the sun. Deep beneath our feet, at the very center of our planet, temperatures reach approximately 10,000 degrees Fahrenheit, comparable to the surface of our star. This inner core, a solid sphere of iron and nickel approximately 1,500 miles across, floats within a larger outer core of molten metal. The extreme heat doesn't melt the inner core because of the immense pressure bearing down upon it. Pressure so intense that despite the tremendous temperature, the atoms remain locked in a solid crystalline structure. This hidden star-hot heart creates Earth's magnetic field, a vast invisible dome that stretches far into space. Like a protective veil, it shields us from solar radiation, deflecting charged particles that would otherwise strip away our atmosphere and bathe the surface in harmful energy. When these particles collide with the magnetic field near the poles, they create the shimmering curtains of light we know as auroras, nature's reminder of the silent battle playing out above our heads. The heat from Earth's core rises slowly through the mantle, the thick layer of partially molten rock that makes up the majority of our planet's volume. This gradual migration of thermal energy drives convection currents, massive circular flows that move at the pace of growing fingernails, yet carry enough force to fracture continents and raise mountain ranges. Heat that originated in Earth's formation, combined with energy released through radioactive decay, maintains this steady churn. A primordial engine that has never stopped running, never faltered in its quiet persistence. We often think of rocks as solid, unchanging things. But to Earth, They are almost fluid, bending, flowing, transforming over immense spans of time. Deep in the mantle, under extraordinary pressure and heat, rock behaves more like extremely thick honey, allowing continents to glide across the surface at a pace too slow for human perception, yet fast enough to completely redraw the map of our world over geological time. Beneath your feet, regardless of where you are right now, the ground is moving. Perhaps only fractions of an inch each year, but moving nonetheless. The floor of your bedroom is drifting gradually across the face of the planet, carried along ancient fault lines and tectonic boundaries. The mountain you admired on your last hike is still growing taller, pushed upward by the same forces that once lifted the seafloor to become the peaks of the Himalayas. The oldest rocks on Earth's surface have witnessed over 4 billion years of planetary history. In remote parts of Canada, Australia, and Greenland, ancient formations called cratons have remained relatively unchanged since the earliest days of our planet's evolution. These venerable stones were already ancient when the first multicellular organisms appeared. They stood witness to skies tinged green with methane, to oceans devoid of fish, to atmospheres without enough oxygen to sustain a single human breath. If these oldest rocks could speak, they might tell of a young Earth bombarded by meteors, of massive impacts that vaporized oceans and reshaped continents. They might describe a moon much closer to our world, appearing 3 times larger in the sky, raising tides that surged miles inland and retreated just as dramatically. They have observed the slow dance of continents, coming together to form supercontinents like Pangaea, then gradually splitting apart again in an endless cycle of planetary reconfiguration. Most of Earth's history has unfolded without human eyes to witness it. For more than 99% of our planet's existence, there were no people to name the mountains or chart the seas. The world turned without us, through ice ages and warming periods, through mass extinctions and evolutionary explosions. It was only in the last fragment of geological time that we appeared, latecomers to a story already billions of years in the telling. Earth has had many faces throughout its long history. Once, a single massive landmass called Rodinia dominated the globe, surrounded by a world-spanning ocean. Later came Pangaea, where all of today's continents were joined in one continuous expanse of land. Africa pressed against North America. India had not yet collided with Asia to raise the Himalayas, and Antarctica nestled against what would become Australia and South America. The Atlantic Ocean did not exist. It was merely a future possibility, a continental seam waiting to split open. Our planet breathes on a timescale too slow for human perception, but it breathes nonetheless. Oxygen cycles through the atmosphere, into oceans, into living things, into stone, and back again. Carbon moves from air to plants, from plants to animals, from all living things back to the soil, and eventually into rock, only to be released again through volcanic activity. These cycles connect everything on Earth, the living and the non-living, the ancient and the new, in a continuous exchange of elements that has persisted for billions of years. Volcanoes are the breathing mouths of our planet. When they erupt, they release gases and minerals that have been trapped below the surface, sometimes for millions of years. A single major eruption can alter global climate patterns, cooling the entire planet by filling the upper atmosphere with reflective particles. The fertile soils around volcanoes, enriched with minerals brought up from deep within the earth, often support some of the most abundant ecosystems on our planet, life thriving at the very doorway of destruction. The deepest place on Earth's surface lies in the western Pacific Ocean. The Challenger Deep, part of the Mariana Trench, plunges nearly 7 miles below sea level, a depth so profound that if Mount Everest were placed at its bottom, the peak would still be more than a mile underwater. The pressure at this depth is over 1,000 times that at sea level, enough to crush a human body instantly. Yet even here, in this extreme environment, life persists. Specialized microbes and strange translucent creatures have adapted to this realm of perpetual darkness and crushing weight. Oceans cover more than 70% of Earth's surface, yet we've mapped less of their depths than the surface of Mars. These vast waters contain mountain ranges longer than any on land, canyons deep enough to swallow entire countries, and underwater volcanoes that erupt unseen beneath miles of seawater. The Mid-Atlantic Ridge, a submarine mountain chain, stretches over 10,000 miles from the Arctic to beyond the southern tip of Africa, the longest mountain range on our planet, with most of it hidden beneath the waves. Within these waters move currents like slow rivers, circulating heat from the tropics toward the poles in patterns that help regulate our climate. The Gulf Stream carries warm water from the Caribbean toward Europe, keeping the British Isles and Scandinavia much warmer than other regions at similar latitudes. Without this oceanic conveyor belt, much of northern Europe would resemble the frozen landscapes of Labrador rather than the temperate climate it currently enjoys. Deep ocean currents move even more slowly, sometimes taking 1,000 years to complete a single circuit of the planet. These abyssal flows are driven by differences in temperature and salinity, creating a three-dimensional circulation pattern of almost unimaginable complexity. Water that sinks in the North Atlantic might not resurface until it reaches the distant Pacific, having traveled along the seafloor for centuries, carrying nutrients and dissolved gases in a planetary cycle as old as the oceans themselves. The water flowing from your tap might contain molecules that once passed through the bloodstream of a dinosaur, or condensed in clouds above ancient forests, where our earliest ancestors took their first steps. Water is Earth's great recycler. It neither appears nor disappears, but simply changes form, moving from ocean to atmosphere, falling as rain, flowing through rivers back to the sea in an endless cycle that has continued since the first rains fell on our young planet. Some of the water on Earth is almost as old as the planet itself. Other droplets formed more recently through the combination of oxygen released by photosynthesis and hydrogen. But regardless of its age, all of Earth's water is connected in a single hydrological system. The same water has been used and reused since before the first cellular life appeared in primordial seas. There is no new water. There is only water endlessly transformed. Soil, often overlooked beneath our feet, is one of Earth's most complex and vital systems. A single teaspoon of healthy soil contains more living organisms than there are people on our planet. These microscopic communities, bacteria, fungi, nematodes, and countless other tiny life forms, break down organic matter, cycle nutrients, filter water, and support the plant life upon which all terrestrial ecosystems depend. Soil is not merely dirt. It is a living skin that covers much of our planet's land surface, as essential to terrestrial life as oceans are to marine creatures. The richest soils on Earth took thousands of years to form, yet can be destroyed in a matter of decades through poor agricultural practices. Topsoil, the most biologically active layer, is created through the slow decomposition of plant and animal matter, combined with the gradual weathering of bedrock below. In the most fertile regions, this precious layer may extend several feet deep. In others, particularly in cold or arid environments, it might be only inches thick, a fragile film upon which entire ecosystems depend. Mountains are not eternal. They rise and fall in cycles that span millions of years. The forces that push them upward, the collision of tectonic plates, the upwelling of magma from below, compete constantly with the forces that wear them down. Rain, wind, frost, and the slow pull of gravity. The Himalayas, Earth's highest mountain range, continue to grow by about 5 millimeters each year as the Indian subcontinent pushes relentlessly into Asia. Meanwhile, the ancient Appalachians of North America, once as tall as the Alps, have been weathering away for more than 300 million years. The Alps themselves tell a story of ancient oceans now vanished. Many of their light-colored limestone peaks were once the floors of tropical seas, teeming with marine life. The fossils of shellfish and coral can still be found near their summits, silent testimony to the immense forces that can lift seabeds into the sky. Similarly, parts of the Sahara Desert were once underwater. Its sands still contain the petrified remains of marine creatures that swam in ancient oceans long before humans walked the earth. Earth's atmosphere, the thin veil of gases that makes life possible, extends for hundreds of miles above the surface, gradually thinning until it merges with the emptiness of space. Yet half of its mass is concentrated in the lowest 5 miles, the layer in which weather occurs, in which birds fly, in which clouds form and dissipate. This lower atmosphere, the troposphere, is remarkably shallow compared to Earth's size, proportionally thinner than the skin of an apple relative to the fruit it protects. Above the troposphere lie additional layers, each with distinct properties. The stratosphere, extending from about 10 to 30 miles up, contains the ozone layer that shields Earth's surface from harmful ultraviolet radiation. Higher still is the mesosphere, where meteors burn up as they enter our atmosphere. Then comes the thermosphere, which can reach temperatures of 3,600 degrees Fahrenheit, though it would not feel hot to human skin because the air molecules are too sparse to transfer much heat. Finally, there is the exosphere, the outermost layer, where the atmosphere fades into space. Forests are Earth's oldest living communities. Long before humans appeared, great woodlands covered much of the land, evolving complex relationships between trees, understory plants, fungi, and animals. The oldest individual trees still living today germinated before the first pyramids were built in Egypt. In Utah, a colony of quaking aspens named Pando shares a single root system that may be over 80,000 years old, making it one of the oldest and largest living organisms on the planet, having survived through ice ages and countless seasons of growth and dormancy. Beneath the forest floor lies an invisible network of fungal threads called mycorrhizae, connecting trees in a vast communication system, sometimes called the Wood Wide Web. Through these fungal connections, trees can share nutrients, send warning signals about insect attacks or disease, and even support younger trees or those growing in less favorable conditions. This underground community creates a kind of collective intelligence, not a conscious mind, but a distributed wisdom that has evolved over millions of years to sustain the forest as a whole. Deserts, despite their apparent emptiness, are teeming with specialized life. Plants and animals have evolved remarkable adaptations to survive in these harsh environments. The saguaro cactus of the Sonoran Desert can live for more than 200 years, slowly growing arms that reach skyward like ancient sentinels. Its shallow but extensive root system can absorb water within minutes of rainfall, storing enough moisture in its expandable tissues to last through months of drought. Desert creatures have similarly evolved to conserve water, from kangaroo rats that can derive all the moisture they need from dry seeds, to camels with their efficient metabolism and heat-regulating adaptations. Earth's oldest desert, the Namib in southern Africa, has remained arid for at least 55 million years, making it the most enduring desert on our planet. Along its western edge, cold air from the Atlantic Ocean meets the hot air of the desert, creating regular fog banks that roll inland. Some organisms here have evolved to harvest water directly from this fog. Beetles that stand on dune crests, collecting moisture on their textured backs, and plants with specialized surfaces that condense and channel water to their roots. The polar regions, Antarctica and the Arctic, are Earth's great refrigerators, reflecting sunlight back into space and cooling the planet. The Antarctic ice sheet, in places over 2 miles thick, contains about 70% of Earth's fresh water and 90% of its ice. If it were to melt completely, global sea levels would rise approximately 200 feet, dramatically redrawing the maps of our continents. This massive weight of ice actually depresses the bedrock beneath it. If the ice were removed, much of Antarctica would slowly rebound upward over thousands of years. Beneath this frozen continent lies Lake Vostok, a massive freshwater lake sealed under the ice for potentially 15 million years. Scientists believe this isolated ecosystem may harbor unique microorganisms that have evolved independently for eons, possibly providing insights into how life might exist in similar environments on icy moons in our solar system. The lake remains largely unexplored, a pristine time capsule from Earth's distant past preserved beneath the frozen surface. Earth's climate has never been static. Over its long history, our planet has experienced periods much warmer and much colder than today. Ice ages have repeatedly advanced and retreated, with glaciers covering much of North America and Europe as recently as 20,000 years ago. During the last major ice age, sea levels were so much lower that humans could walk from Siberia to Alaska across the land bridge of Beringia, populating the Americas for the first time. In contrast, during the warmest periods of Earth's history, crocodile-like reptiles swam in Arctic waters, and Antarctica was covered with temperate forests rather than ice. These natural climate fluctuations have been driven by various factors: slight variations in Earth's orbit and axial tilt, changes in solar output, continental drift altering ocean currents, and volcanic activity releasing or sequestering carbon dioxide. What makes current climate change different is both its rate, occurring over decades rather than millennia, and its cause, primarily the rapid release of carbon that had been locked away in fossil fuels for millions of years. Earth's magnetic field is not fixed, but constantly shifting. The magnetic North Pole, toward which all compasses point, moves at a rate of about 30 miles per year, requiring navigational charts to be regularly updated. More dramatically, the entire magnetic field has reversed completely hundreds of times throughout Earth's history, with magnetic north becoming south and vice versa. These reversals are preserved in the rocks of the ocean floor, creating a striped pattern of normal and reversed polarity that has helped scientists understand the process of seafloor spreading and continental drift. During these magnetic reversals, which can take thousands of years to complete, Earth's protective magnetic shield weakens, potentially allowing more solar radiation to reach the surface. Interestingly, no mass extinctions have been conclusively linked to these events, suggesting that life has always found ways to adapt to the changing conditions. Currently, Earth's magnetic field is weakening faster than expected, leading some scientists to speculate that we may be in the early stages of another reversal, though it would likely take thousands of years to complete. Life itself has shaped Earth as much as physical forces have. The oxygen we breathe did not exist in significant quantities in Earth's early atmosphere. It was generated over billions of years by photosynthetic bacteria and later by plants, completely transforming the chemistry of our air and oceans. This great oxygenation event, beginning around 2.5 billion years ago, was actually toxic to many of the anaerobic organisms that had dominated Earth until then, causing one of the first major extinction events in our planet's history. Similarly, the White Cliffs of Dover in England and similar chalk formations around the world were created by countless generations of tiny marine organisms that extracted calcium carbonate from seawater to build their shells. When these creatures died, their microscopic remains accumulated on the seafloor, eventually forming thick deposits that were later lifted above sea level by geological forces. What appears to us as simple white rock is actually a vast cemetery of ancient ocean life. Billions upon billions of tiny shells compressed over millions of years. Earth experiences approximately 500,000 detectable earthquakes each year. Most are so minor that only sensitive instruments can record them, but around 100,000 can be felt by humans, and only about 100 cause significant damage. These tremors occur primarily along fault lines where tectonic plates meet, though intraplate earthquakes can also occur within stable continental regions, often puzzling scientists with their unexpected locations. The largest earthquake ever recorded by modern instruments struck Chile in 1960, measuring approximately 9.5 on the Richter scale. It generated tsunamis that traveled across the entire Pacific Ocean, causing damage as far away as Hawaii, Japan, and the Philippines. The energy released by this single event exceeded the combined power of all the bombs detonated during World War II, including both atomic weapons. Yet such powerful events are merely moments in Earth's ongoing geological processes, neither the beginning nor the end of the planet's constant transformation. Tsunamis, those devastating ocean waves triggered by undersea earthquakes or landslides, can travel across entire ocean basins at speeds approaching 500 miles per hour. In deep water, they may be barely noticeable, perhaps only a foot or two high and many miles between crests. But as these waves approach shallow coastal waters, They slow down and grow taller, sometimes reaching heights of 100 feet or more before crashing onto shore with catastrophic force. The Indian Ocean tsunami of 2004, triggered by a massive undersea earthquake near Sumatra, traveled thousands of miles and affected coastlines across multiple countries, demonstrating how events in one part of our interconnected planet can impact regions far away. Lightning strikes Earth approximately 8 million times each day. These brilliant discharges of atmospheric electricity briefly heat the air around them to temperatures 5 times hotter than the surface of the sun. Lightning has played a crucial role in Earth's chemistry, helping to create complex organic compounds in the early atmosphere that may have contributed to the origin of life. Even today, lightning fixates atmospheric nitrogen into forms that plants can use, naturally fertilizing soils around the world. Some lightning strikes create fulgurites, glassy tubes formed when bolts melt and fuse sandy soil. These strange formations, sometimes called fossilized lightning, preserve the path of a lightning strike through the ground. They can extend several feet deep and branch in multiple directions, creating a physical record of an event that lasted less than a second. Fulgurites found today may have formed thousands of years ago, silent testimony to ancient storms long forgotten. Caves represent Earth's quiet artistry, spaces where water sculpts stone with infinite patience. The largest cave systems extend for hundreds of miles through layered limestone, creating subterranean worlds with their own unique ecosystems. Kentucky's Mammoth Cave, with over 400 miles of surveyed passages, is the longest known cave system on Earth, though others in Vietnam, Mexico, and China feature individual chambers so vast they could enclose several football fields or even accommodate flying helicopters within their cavernous expanses. The formations found in caves, stalactites hanging like stone icicles from the ceiling, stalagmites rising like frozen fountains from the floor, grow at extraordinarily slow rates, sometimes taking a century to add just a single inch. The largest of these formations represent tens of thousands of years of continuous development, mineral-laden water depositing calcium carbonate one microscopic layer at a time. Some ancient caves contain crystals of gypsum that have grown to lengths of over 30 feet. Their geometric perfection developing in darkness and stillness over hundreds of thousands of years. Rivers are the veins of our continents, channels through which water, sediment, nutrients, and even heat flow across the landscape. The Amazon River discharges more water than the next 7 largest rivers combined, pouring so much fresh water into the Atlantic Ocean that sailors can sometimes drink from the sea surface more than 100 miles offshore. This mighty river system drains a basin covering about 40% of South America, its countless tributaries collecting rainfall from vast forests and distant mountain ranges in a watershed of almost unimaginable complexity. Rivers are impermanent features in geological terms. They change course, carve new channels, or disappear entirely as landscapes evolve. The Mississippi River has shifted its path to the Gulf of Mexico many times throughout history, leaving behind oxbow lakes and abandoned channels across its floodplain. Without human intervention through levees and control structures, it would likely have already changed course again, finding a shorter path to the sea through what is now the Atchafalaya River in Louisiana. A reminder that even the mightiest rivers exist in dynamic equilibrium with the landscapes they shape. Earth's biodiversity, the incredible variety of living organisms that share our planet, represents billions of years of evolutionary history. Scientists have formally described about 2 million species, from microscopic bacteria to towering sequoias, from tiny insects to massive whales. Yet this known diversity likely represents less than 20% of the total number of species alive today. The greatest diversity lies in tropical rainforests, where a single acre might contain more tree species than exist in all of North America, and in the deep oceans, where new forms of life are discovered with almost every research expedition. This biodiversity is not evenly distributed across our planet. Certain regions, known as biodiversity hotspots, contain exceptional concentrations of endemic species, those found nowhere else on Earth, often in areas facing significant human impact. These hotspots, which include places like Madagascar, the tropical Andes, and the forests of Southeast Asia, collectively cover less than 3% of Earth's land surface, yet contain more than 50% of the world's plant species and an even higher proportion of many animal groups. The smallest organisms on Earth have had perhaps the greatest impact on its development. Bacteria, archaea, and other microbes make up most of the planet's biomass and genetic diversity. They were the first life forms to appear over 3.5 billion years ago, and they have shaped Earth's systems ever since, creating oxygen, cycling nutrients, forming soils, and establishing symbiotic relationships with larger organisms. Even the human body contains more bacterial cells than human ones, a reminder that we exist not as isolated individuals, but as complex ecosystems of cooperation and interdependence. Some bacteria live in environments so extreme they were once thought to be uninhabitable. In scalding hot springs, in the crushing depths of ocean trenches, in highly acidic waters, or deep within Earth's crust, where they survive on chemical energy rather than sunlight. These extremophiles push the boundaries of what we consider possible for life, suggesting that living organisms might exist in seemingly hostile environments on other worlds, such as beneath the ice of Jupiter's moon, Europa, or in the subsurface aquifers of Mars. Fungi represent one of Earth's great success stories, a kingdom of life distinct from both plants and animals that includes everything from microscopic yeasts to vast mycelial networks that can spread for miles beneath the forest floor. The largest known organism on Earth is actually a honey fungus in Oregon's Blue Mountains, covering nearly 4 square miles and estimated to be between 2,000 and 8,000 years old. This immense living system consists mostly of thread-like hyphae growing underground, with only the occasional mushroom, the fungal equivalent of fruit, appearing above the surface. Fungi are Earth's great decomposers, breaking down dead organic matter and recycling its components back into the ecosystem. Without them, fallen leaves and dead wood would accumulate indefinitely, locking away nutrients needed for new growth. Some fungi have evolved mutualistic relationships with plants, forming the mycorrhizal networks mentioned earlier that connect individual trees in forest communities. Others have developed powerful enzymes capable of digesting materials as tough as wood, bone, or even certain plastics, highlighting their remarkable metabolic versatility. The oceans contain approximately 97% of Earth's water, and these vast basins have their own landscapes as diverse as those on land. The longest mountain range on Earth, the mid-ocean ridge system, winds through all major oceans like a seam along a baseball, stretching for more than 40,000 miles. Along these underwater mountains, new seafloor is constantly being created as magma wells up from below and cools, pushing older crust outward in a process called seafloor spreading. Near these mid-ocean ridges, in the perpetual darkness of the deep sea, remarkable ecosystems thrive around hydrothermal vents, fissures in the seafloor that release superheated, mineral-rich water. These black smokers support communities of organisms that exist independently of sunlight, deriving energy instead from the chemicals in the vent fluid through a process called chemosynthesis. Giant tube worms, blind shrimp, and unique microbial mats flourish in these extreme environments, offering glimpses of how life might exist on worlds without access to starlight. The deepest parts of the ocean remain largely unexplored, a frontier on our own planet more inaccessible in many ways than the surface of the moon. The crushing pressure in the deepest trenches, more than 8 tons per square inch, makes exploration extraordinarily difficult. Yet even in these extreme environments, life persists. Specialized fish with translucent skin, bioluminescent organs, and pressure-adapted biochemistry move through the darkness. Strange crustaceans scavenge the seafloor, while bacteria with unique metabolic pathways extract energy from the sparse nutrients available in these isolated habitats. Coastal zones, where land meets sea, are among Earth's most productive ecosystems. Estuaries, those partially enclosed bodies of water where rivers meet the ocean, serve as nurseries for countless marine species. The mixing of fresh and salt water creates a gradient of conditions that supports remarkable biodiversity, from microscopic plankton to juvenile fish that will later migrate to the open ocean. Salt marshes and mangrove forests along tropical and subtropical coastlines not only nurture young marine life, but also protect the land from storm surges and erosion, demonstrating the intricate interconnectedness of terrestrial and marine systems. Coral reefs, often called the rainforests of the sea, occupy less than 1% of the ocean floor, yet harbor approximately 25% of all marine species. These living structures are built primarily by tiny colonial animals called coral polyps, which secrete calcium carbonate skeletons that accumulate over centuries to form massive reefs. The Great Barrier Reef off Australia's coast, visible even from space, consists of nearly 3,000 individual reefs and hundreds of islands stretching for over 1,400 miles, the largest structure on Earth created by living organisms. Within these reefs exists a world of extraordinary complexity and beauty. Fish in impossible colors dart among the coral branches. Octopuses change both color and texture to match their surroundings with uncanny precision. Cleaner shrimp set up stations where larger fish come to have parasites removed in a remarkable example of interspecies cooperation. The biodiversity of healthy coral reefs rivals that of tropical rainforests, with thousands of species interacting in networks of competition, cooperation, and mutual dependence that scientists are still working to fully understand. Earth's history is written in stone for those who know how to read it. The science of stratigraphy, the study of rock layers, allows geologists to reconstruct ancient environments and events with remarkable precision. In places like the Grand Canyon, where the Colorado River has carved through nearly 2 billion years of Earth's history, the exposed rock walls tell stories of ancient seas, coastal swamps, wind-blown deserts, and lush floodplains that once occupied the same location at different points in deep time. Fossils preserved within these rock layers provide glimpses of life's evolution, from the simplest bacterial mats that left fine layers in ancient stones to the complex shells, bones, and occasionally even soft tissues of more recent organisms. The sudden disappearance of certain fossils from the record, followed by the appearance of new forms, marks the boundaries between geological periods and often corresponds to major extinction events, when significant portions of Earth's biodiversity disappeared in relatively short spans of time. The most dramatic of these mass extinctions occurred approximately 252 million years ago, at the end of the Permian period. This great dying eliminated roughly 90% of marine species and 70% of terrestrial vertebrates, a planetary catastrophe likely triggered by massive volcanic eruptions in what is now Siberia. These eruptions released enormous quantities of greenhouse gases, dramatically warming the climate and acidifying the oceans. The world that emerged after this event was fundamentally different, setting the stage for the rise of dinosaurs and eventually mammals. More familiar is the extinction event that ended the reign of non-avian dinosaurs 66 million years ago, most likely caused by the impact of an asteroid or comet approximately 6 miles in diameter. The collision site, now known as the Chicxulub crater, lies beneath Mexico's Yucatan Peninsula. This impact released energy equivalent to billions of atomic bombs, causing tsunamis, global wildfires, and eventually a prolonged impact winter as dust and aerosols blocked sunlight for years. The dramatic cooling, followed by intense warming as greenhouse gases accumulated, created conditions that favored the survival of small, adaptable mammals, including the lineage that would eventually lead to humans. We sometimes forget that our planet is not static, but constantly changing, with new land being created even as older formations are worn away. Along the mid-Atlantic ridge, Iceland stands as a visible example of this ongoing process, a landmass being formed as the North American and Eurasian plates move apart. The island grows by about 2 centimeters per year as new volcanic material wells up from below, gradually adding to its eastern and western edges. What we see today is merely the most recent chapter in an ongoing story of creation. Similarly, the Hawaiian Islands represent a different type of volcanic formation, a chain created as the Pacific Plate moves over a relatively stationary hotspot in Earth's mantle. The oldest islands in the chain, now eroded and subsided beneath the waves as atolls, formed over 70 million years ago. The youngest, Hawaii's Big Island, continues to grow through active volcanism. And beneath the ocean surface, a new island called Loihi is already forming, expected to rise above sea level in perhaps 50,000 years. A reminder that Earth's geography is merely a snapshot in an endless process of transformation. Human existence represents just a tiny fraction of Earth's history, less than 0.5% of the time since life first appeared. If we compressed Earth's 4.5 billion year history into a single year, humans in our modern form would appear only in the last few minutes before midnight on December 31st. Yet in that brief moment, we have become a geological force in our own right, moving more soil and rock annually than all of Earth's rivers combined, altering atmospheric chemistry at rates unprecedented in the planet's long history, and initiating what many scientists now call the Anthropocene, a new geological epoch defined by human influence. This influence extends to even the most remote corners of our planet. Microplastics have been found in Arctic ice cores and at the bottom of the Mariana Trench. Industrial chemicals persist in the tissues of animals living far from any factory. Carbon dioxide released from burning fossil fuels has altered the chemistry of the entire atmosphere. These changes have occurred with remarkable speed in geological terms, most within the past century or so, demonstrating both the extent of human impact and the interconnectedness of Earth's systems. Yet Earth has experienced dramatic changes before. It has survived asteroid impacts, supervolcanic eruptions, and radical shifts in climate. Life has persisted through 5 major mass extinction events, each time recovering and diversifying, though this process took millions of years. The planet itself will continue long after humans have disappeared, whether we manage to create a sustainable relationship with Earth systems or drive ourselves and many other species to extinction through our actions. What remains uncertain is not Earth's survival, but our own. Some of Earth's most striking landscapes have formed in relatively recent geological time. Yellowstone's geothermal features, its geysers, hot springs, and mud pots, are powered by a massive magma chamber that has produced 3 enormous eruptions over the past 2 million years, the most recent only 640,000 years ago. This is extraordinarily recent in geological terms, and the same volcanic system remains active today, slowly inflating and deflating as magma shifts beneath the surface. Yellowstone is not merely a scenic wonder, but a window into Earth's restless interior, a reminder of the tremendous energies that continue to shape our planet. The Grand Canyon offers another perspective on Earth's recent geological activity. Though the Colorado River began carving this immense gorge only 5 to 6 million years ago, a mere moment in planetary terms, the rocks it has exposed span nearly half the age of Earth itself. The oldest layers at the canyon bottom formed almost 2 billion years ago, when the only life on our planet consisted of single-celled organisms floating in primordial seas. As you move upward through the canyon walls, you travel forward in time, each stratum representing a different chapter in Earth's evolving story. Ancient beaches, swamps, deserts, and shallow seas that once covered what is now the southwestern United States. What makes landscapes like the Grand Canyon so remarkable is not just their beauty, but their ability to compress time, making billions of years of planetary history visible in a single view. The layers of red, orange, and tan rock tell stories of advancing and retreating oceans, of mountains rising and being worn away, of climate shifting from tropical to arid and back again. And through it all, life was evolving, becoming more complex, adapting to each new environment as Earth itself transformed around it. Some of Earth's most striking features form with extraordinary speed in geological terms. The Richat structure in Mauritania, sometimes called the Eye of the Sahara, appears from space as a perfect bullseye of concentric rings spanning nearly 30 miles across. Once thought to be an impact crater, geologists now believe it formed when a dome of rock pushed upward and then eroded, exposing layers of different rock types that erode at varying rates. Though it likely took millions of years to reach its current form, this is still remarkably fast compared to many geological processes that require hundreds of millions of years to unfold. Similarly, the white sands of New Mexico, the world's largest gypsum dune field, began forming only about 10,000 years ago, after the last ice age. As a large lake dried up, it left behind gypsum deposits that were eventually broken down into sand-sized particles and blown by the wind into the dazzling white dunes we see today. These pristine dunes continue to move and shift, migrating across the landscape at rates of up to 30 feet per year, creating an ever-changing topography that seems timeless yet is constantly in motion. Earth's relationship with water has shaped nearly every aspect of its surface. The planet exists in a remarkable state of equilibrium, where water can exist simultaneously as a solid, liquid, and gas, a condition found on few other worlds in our solar system. This unique circumstance has allowed water to become the primary sculptor of our landscapes, whether through the steady erosion of flowing rivers, the slow grinding of glacial ice, or the patient dissolution of limestone to form vast cave systems. Underground, water has created some of Earth's most mesmerizing environments. Carlsbad Caverns in New Mexico formed over millions of years as sulfuric acid dissolved the surrounding limestone, creating more than 100 chambers, including one large enough to hold 14 football fields. In this enormous room, which early explorers named the Big Room, delicate stalactites hang from the ceiling like stone icicles, while stalagmites rise from the floor in an endless variety of shapes and sizes. These formations grow with extraordinary slowness. A typical stalactite might extend by only a fraction of an inch over a human lifetime, making the immense formations found in caves across the world silent testimony to the passage of vast spans of time. Some caves contain even more extraordinary features. Mexico's Cave of Crystals, discovered beneath the Chihuahuan Desert in 2000, contains gypsum crystals up to 36 feet long and weighing as much as 55 tons. These enormous crystal beams formed over hundreds of thousands of years in a chamber filled with mineral-rich water maintained at a constant temperature. When mining operations pumped out this water, they revealed a scene that seemed to belong to another world. A forest of massive transparent crystals crossing the chamber in all directions, creating a geometric marvel that had developed in perfect darkness and stillness for millennia. In Slovenia's Postojna cave system, a species of salamander called the olm has adapted so completely to the perpetual darkness that it has essentially stopped developing eyes. These pale, slender amphibians can live for over a century and can survive without food for up to 10 years, having evolved to match the slow, unchanging rhythm of their subterranean home. Their presence reminds us that life finds ways to adapt to even the most challenging environments Earth offers, often developing extraordinary specializations over evolutionary time. Even the deepest parts of Earth's crust harbor life. Microorganisms have been found living more than a mile beneath the surface, surviving on chemical energy rather than sunlight. Some of these extremophiles thrive in conditions that would be lethal to surface-dwelling organisms, in highly acidic or alkaline environments, in water hot enough to boil at the surface, or under pressures that would crush most forms of life. The existence of this deep biosphere has expanded our understanding of where life can exist and has implications for the search for life on other worlds, suggesting that organisms might survive in subsurface environments on planets that appear hostile on their surfaces. Moving from beneath the ground to high above it, Earth's atmosphere represents another realm of constant transformation. The clouds that drift across our skies contain countless billions of water droplets or ice crystals, each one forming around a tiny particle of dust, pollen, or even a microorganism. These vast, ephemeral structures, sometimes weighing millions of tons, yet floating effortlessly above us, are in constant flux, forming, dissipating, and reforming in endless cycles driven by the sun's energy and Earth's rotation. Some clouds assume forms of extraordinary beauty and complexity. Mammatus clouds, with their distinctive pouch-like structures, often appear after severe thunderstorms, hanging from the underside of the anvil cloud like bubbles or globes. Lenticular clouds, shaped like stacked lenses or flying saucers, form over mountains when moist air flows over the peaks and condenses in the lee of the obstruction. Though the cloud remains stationary relative to the mountain, the air actually flows through it continuously, condensing on one side and evaporating on the other. A perfect example of dynamic stability, where something appears unchanging while being in constant motion. Perhaps most dramatic are the towering cumulonimbus clouds that can reach heights of over 10 miles, their tops spreading out against the stratosphere to form the distinctive anvil shape of severe thunderstorms. Within these massive structures, complex dynamics create extraordinary phenomena. Powerful updrafts and downdrafts, the separation of electrical charges that leads to lightning, and the formation of hail as ice particles cycle up and down through different temperature zones, adding new layers of ice with each pass. These clouds represent atmospheric energy on a massive scale, sometimes releasing more power in a single storm than a small nuclear weapon. Weather patterns connect distant parts of our planet in ways that aren't immediately obvious. The El Niño Southern Oscillation, a cyclical warming and cooling of surface waters in the central and eastern Pacific Ocean, affects rainfall patterns as far away as Africa and Europe. When warm water shifts eastward during El Niño events, it alters atmospheric circulation globally, bringing drought to some regions while drenching others in unexpected rainfall. This pattern has occurred naturally for thousands of years, with evidence of its effects found in ice cores, tree rings, and coral growth bands around the world. Similarly, the jet streams, fast-flowing air currents in the upper atmosphere, create connections between widely separated regions. The polar jet stream, flowing from west to east at altitudes of about 5 to 9 miles, can reach speeds exceeding 200 miles per hour and plays a crucial role in determining weather patterns across North America, Europe, and Asia. When this atmospheric river develops large meanders, it can pull Arctic air far to the south or push tropical warmth into normally temperate regions, creating the conditions for extreme weather events. Earth's seasons, which so profoundly influence life in the middle and high latitudes, result from a simple astronomical reality: the tilt of our planet's axis relative to its orbital plane. This axial tilt of approximately 23.4 degrees means that as Earth travels around the Sun, different hemispheres receive varying amounts of direct sunlight. Without this tilt, we would experience no seasons at all. Each latitude would receive the same amount of sunlight year-round, creating a more static climate pattern globally. The current degree of axial tilt is not fixed, but varies over cycles lasting about 41,000 years, ranging from about 22.1 to 24.5 degrees. When the tilt is greater, seasonal differences become more pronounced. When it is smaller, seasons become milder. This cyclical variation, combined with changes in Earth's orbital shape and the gradual precession of the axial rotation, like the wobble of a spinning top, creates long-term climate patterns known as Milankovitch cycles, named after the Serbian scientist who first calculated their effects on Earth's climate. Among Earth's most majestic atmospheric displays are the auroras, the northern and southern lights. These shimmering curtains of color occur when charged particles from the sun, carried by the solar wind, interact with gases in our upper atmosphere. Guided by Earth's magnetic field, these particles spiral toward the polar regions, where they collide with oxygen and nitrogen atoms, causing them to emit light in characteristic colors, typically green and red for oxygen, blue and purple for nitrogen. The result is a dancing light show that has inspired awe and mythology for thousands of years of human history. The auroras reveal the invisible connection between Earth and the Sun, a relationship that shapes many aspects of our planet's systems. The solar wind, a stream of charged particles continuously flowing outward from the Sun, would strip away Earth's atmosphere over time if not for our protective magnetic field. This invisible shield, generated by the movement of molten iron in Earth's outer core, deflects most of these particles, allowing life to flourish on our planet's surface. Mars, which lost its global magnetic field billions of years ago, gradually lost most of its atmosphere to space, transforming from a world with flowing water to the cold, dry planet we see today. Earth's oceans are in constant motion, not only through the visible action of waves and tides, but through deep currents that circle the planet like a global conveyor belt. This thermohaline circulation, driven by differences in temperature and salinity, moves enormous volumes of water between the equator and the poles, between the surface and the abyss. A drop of water that sinks in the North Atlantic might not return to the surface for 1,000 years, having traveled through the deep ocean basins of the world, gradually mixing with other waters and carrying heat and nutrients in a planetary cycle of remarkable complexity. Ocean currents influence climate in profound ways. Western Europe enjoys temperatures significantly warmer than regions at similar latitudes in North America, largely because of the Gulf Stream, which carries tropical warmth northeastward across the Atlantic. Similarly, the Kuroshio Current moderates the climate of Japan, while the cold California Current brings cooling fog to San Francisco during summer months. These oceanic rivers, flowing within the larger body of seawater, create connections between distant regions and help distribute heat more evenly across our planet. The ocean surface is in constant dialogue with the atmosphere above it, exchanging heat, moisture, and gases in a dynamic relationship that drives much of our weather and climate. Each year, the ocean absorbs approximately 25% of the carbon dioxide released by human activities, gradually changing its chemistry in a process called ocean acidification. This absorption has slowed the pace of atmospheric warming, but comes at a cost to marine ecosystems, particularly those built around calcium carbonate structures like coral reefs and the shells of many marine organisms. Deep beneath the ocean surface, where sunlight never penetrates, Earth continues to create new crust along the mid-ocean ridges, submarine mountain chains that mark the boundaries between diverging tectonic plates. Here, magma wells up from the mantle, cooling to form new seafloor that slowly spreads outward at rates of 1 to 6 inches per year. This process continuously renews the ocean floor. Most of the current seafloor is less than 200 million years old, relatively young in geological terms. The oldest continental crust, by comparison, has survived for over 4 billion years. Near these mid-ocean ridges, some of Earth's most extreme environments host unique ecosystems. Hydrothermal vents, fissures in the seafloor from which superheated, mineral-rich water emerges, support communities of organisms that exist independently of sunlight. Instead of photosynthesis, these ecosystems are based on chemosynthesis, with specialized bacteria deriving energy from the chemical compounds in the vent fluid. These bacteria then support larger organisms, including giant tube worms with bright red plumes, blind shrimp with light-sensing patches on their backs, and unique species of fish adapted to the warm, mineral-rich waters. The discovery of these deep-sea hydrothermal communities in the 1970s revolutionized our understanding of where and how life can exist. It demonstrated that ecosystems could be based on geochemical energy rather than sunlight, expanding our concept of habitable environments, both on Earth and potentially on other worlds. Some scientists now speculate that life might have originated near such vents, where the chemistry, energy sources, and physical conditions could have facilitated the formation of the complex molecules necessary for life. The deep ocean remains one of Earth's least explored frontiers. We have more detailed maps of the surface of Mars than of our own ocean floor, despite the fact that it covers more than 70% of our planet. Each research expedition to the deep sea discovers new species and sometimes entirely new categories of organisms. The Census of Marine Life, a decade-long international effort completed in 2010, identified more than 6,000 potentially new species, yet estimated that at least 1 million more marine species remain undiscovered. A reminder of how much we still have to learn about our own planet. Some of the most mysterious ocean phenomena occur at the mesophotic zone, the middle light zone extending from about 100 to 300 feet below the surface. Here, enough sunlight penetrates to support photosynthesis, but conditions are dramatically different from the familiar shallow reef environments. Specialized corals, sponges, and algae have adapted to the dim blue light, often developing unique pigmentation to capture the available wavelengths. These mesophotic ecosystems may serve as refuges for species under pressure in shallower waters and could be sources of larvae to repopulate damaged reefs, a kind of depth-based resilience built into marine ecosystems. Moving from water to land, Earth's surface hosts an extraordinary diversity of ecosystems, each adapted to particular combinations of temperature, rainfall, soil type, and other environmental factors. Tropical rainforests, which cover less than 7% of Earth's land surface, contain more than 50% of the world's plant and animal species. A single hectare of rainforest might contain more than 200 tree species, more than in all of North America, along with thousands of insect species, hundreds of birds, and dozens of mammals, reptiles, and amphibians. These forests represent not just collections of species, but complex networks of relationships developed over evolutionary time. Many tropical plants can only be pollinated by specific insects or birds. Certain fruits can only be dispersed by particular animals. Some trees can only germinate after passing through the digestive tract of a specialized fruit eater. Remove one element from this intricate web, and the effects cascade through the entire system in ways that are difficult to predict, but often lead to further losses and simplification of the ecosystem. The boreal forests that stretch across northern North America, Scandinavia, and Russia represent a very different kind of ecosystem, one dominated by a relatively small number of conifer species adapted to cold temperatures and short growing seasons. These vast forests, also called the taiga, cover approximately 17% of Earth's land surface and contain more than 30% of all carbon stored in terrestrial ecosystems. Their dark evergreen needles absorb sunlight even in winter, warming the local environment and helping to maintain regional climate patterns. Despite their apparent uniformity when viewed from above, boreal forests contain remarkable microscale diversity. The forest floor is a mosaic of lichens, mosses, and small flowering plants, many of which have developed specialized relationships with the dominant trees. Fungi form extensive networks in the soil, connecting individual trees and facilitating the exchange of nutrients and information. Wildlife adapted to these northern forests include specialists like the moose, which can digest the tough, resinous browse that most other herbivores avoid, and the lynx and snowshoe hare, whose populations cycle in a famous predator-prey relationship that echoes across the landscape. Grasslands occupy approximately a quarter of Earth's land surface and occur on every continent except Antarctica. These ecosystems, including the prairies of North America, the steppes of Central Asia, and the savannas of Africa, are dominated by grasses and other non-woody plants adapted to moderate precipitation, frequent fires, and often grazing by large herbivores. The deep, fibrous root systems of prairie plants can extend more than 15 feet into the soil, creating some of the richest agricultural lands on Earth and storing immense quantities of carbon. Before human agricultural development, vast herds of grazing animals migrated across many of these grasslands, following seasonal patterns of rainfall and plant growth. These movements, whether of bison across the American Great Plains, wildebeest across the Serengeti, or saiga antelope across the Eurasian steppe, represented not just spectacular wildlife displays, but critical ecological processes. The grazing, trampling, and fertilizing activities of these herds helped maintain the grassland character of these ecosystems, preventing the encroachment of woody vegetation and cycling nutrients through the landscape. Deserts, which occupy about a third of Earth's land surface, demonstrate life's remarkable adaptability to extreme conditions. These arid regions, defined by their low precipitation, typically less than 10 inches annually, experience some of the most dramatic temperature fluctuations on Earth, sometimes ranging from freezing at night to well over 100 degrees Fahrenheit during the day. Yet even here, in what might seem like the most inhospitable environments, life has found ways to persist and even thrive through extraordinary specialization. Desert plants display a remarkable array of adaptations to conserve water and withstand heat. Cacti and other succulents store water in modified stems or leaves, while their spines both provide shade and deter thirsty animals. Many desert plants have extensive but shallow root systems that can quickly absorb moisture after rare rainfall events. Others remain dormant as seeds for years, germinating only when conditions are favorable. Some, like the remarkable resurrection plant, can dry out completely, appearing dead for months or even years, then quickly revive and turn green within hours of rainfall. Desert animals display equally impressive adaptations. The kangaroo rat of North American deserts can obtain all the water it needs from the dry seeds it eats, never needing to drink liquid water. The fennec fox of the Sahara has enormous ears that serve as radiators, dissipating body heat during the cool desert night. Many desert insects and reptiles have developed specialized scales or waxy coatings that minimize water loss through their skin. Others avoid the heat altogether by remaining underground during the day, emerging only at night when temperatures are more moderate. Perhaps the most remarkable desert adaptation is seen in extremophile microorganisms that inhabit the driest places on Earth, such as Chile's Atacama Desert. Some of these organisms can survive in a dormant state for decades with essentially no water, then quickly resume metabolic activity when moisture becomes available. Others have evolved to extract water from the air during rare fog events or to live within salt crystals, using the salt's hygroscopic properties to gather moisture. These microorganisms push the boundaries of what we consider possible for life, suggesting that living things might survive in seemingly hostile environments on other worlds. Wetlands, including marshes, swamps, and bogs, represent some of Earth's most productive ecosystems, despite covering only about 6% of its land surface. These transitional zones between terrestrial and aquatic systems act as natural water filters, removing pollutants and excess nutrients from water flowing through them. They serve as critical habitat for countless species of birds, fish, amphibians, and insects, including many that migrate between different ecosystems during their life cycles. And they store enormous amounts of carbon in their soils and vegetation, playing a disproportionately large role in regulating atmospheric carbon dioxide levels. Peatlands, a particular type of wetland found primarily in northern regions and tropical lowlands, are especially important carbon repositories. Though they cover only about 3% of Earth's land surface, they store approximately 30% of all soil carbon, more than twice the amount held in all the world's forests combined. These water-saturated environments prevent organic matter from fully decomposing, allowing it to accumulate over thousands of years as peat. Some northern peatlands have been slowly storing carbon since the end of the last ice age, creating deposits more than 20 feet deep in some locations. Earth's mountainous regions, which occupy approximately 24% of the global land surface, create some of the planet's most diverse ecosystems. As elevation increases, temperature and atmospheric pressure decrease, while exposure to ultraviolet radiation increases, creating dramatic environmental gradients compressed into relatively short distances. A traveler ascending a tropical mountain might pass through lowland rainforest, cloud forest, elfin woodland, and alpine meadows before reaching barren rocky slopes near the summit. each zone with its own distinctive community of plants and animals adapted to specific conditions. Mountains also create their own weather patterns and influence regional climates. As air masses encounter these elevated barriers, they are forced upward, cooling as they rise and often releasing moisture on windward slopes. This orographic precipitation creates some of Earth's wettest environments on the windward sides of mountain ranges, while casting rain shadows on the leeward sides that can lead to desert conditions. The Sierra Nevada of California dramatically demonstrates this effect, with lush western slopes and the arid Great Basin to the east. Islands represent natural laboratories for evolution, places where organisms have developed in isolation from mainland populations, often taking unique evolutionary paths. The most famous example is the Galapagos Archipelago, where Charles Darwin observed distinct varieties of finches, tortoises, and other animals on different islands. Observations that helped inspire his theory of evolution by natural selection. Similar patterns of adaptive radiation, where a single ancestral species diversifies to fill multiple ecological niches, have occurred on island chains worldwide, from Hawaii to Madagascar to the Caribbean. This isolation makes island ecosystems particularly vulnerable to disturbance. Species that evolved without mammalian predators often lack defensive adaptations and may be easily overtaken when new predators are introduced. Plants that developed without browsing pressure from large herbivores may lack chemical or physical defenses. These vulnerabilities have made islands hotspots for extinction in recent centuries, as human activities have disrupted the isolation that shaped these unique evolutionary pathways. Earth's polar regions, the Arctic and Antarctic, represent some of the planet's most extreme environments, yet support remarkably adapted ecosystems. The Antarctic continent, almost entirely covered by ice averaging more than a mile thick, might seem inhospitable to life, yet its coastal regions support millions of penguins, seals, and seabirds, while its surrounding ocean teems with krill, fish, and whales. Even the ice sheet itself harbors microbial communities in isolated lakes beneath its surface and within tiny brine channels in the ice itself. The Arctic, a primarily ocean environment surrounded by continental land masses, presents different challenges for life. Unlike Antarctica, which has no native land mammals, the Arctic supports polar bears, musk oxen, caribou, Arctic foxes, and many other species adapted to extreme cold. Many have evolved insulating layers of fat and fur, reduced extremities to minimize heat loss, and specialized blood vessels that allow them to maintain different temperatures in their core and extremities. Some, like the Arctic ground squirrel, can allow their body temperature to drop below freezing during hibernation without forming destructive ice crystals in their tissues, a feat of physiological adaptation that continues to amaze scientists. Earth's soils represent one of its most complex and least appreciated systems, not merely dirt, but living ecosystems with more biodiversity than the forests or oceans above them. A single handful of healthy soil contains billions of bacteria, yards of fungal filaments, thousands of protozoa, and dozens of nematodes, mites, and other microarthropods, all interacting in complex food webs that decompose organic matter, cycle nutrients, store carbon, filter water, and support plant growth. Different soils develop under different environmental conditions, creating distinct types with varying properties. The rich, black Chernozem soils of grasslands, built over thousands of years by the deep roots of prairie plants, contain high levels of organic matter and nutrients. The red, iron-rich laterites of tropical regions, heavily leached by abundant rainfall, may be nutrient-poor but effectively store carbon. The thin, rocky soils of mountainous regions might seem unproductive, yet support specialized plant communities adapted to these challenging conditions. Each soil type represents not just a different medium for plant growth, but a unique ecosystem that has co-evolved with the plants, animals, and microorganisms that inhabit it. Some soil organisms form remarkable partnerships with plants. Mycorrhizal fungi, which associate with the roots of most land plants, essentially extend the plant's root system, helping it access water and nutrients in exchange for carbohydrates produced through photosynthesis. Nitrogen-fixing bacteria form nodules on the roots of legumes and certain other plants, converting atmospheric nitrogen into forms the plant can use. A symbiotic relationship that has allowed legumes to thrive in nitrogen-poor environments and has made them valuable in agricultural systems for thousands of years. Earth's biological and geological systems are intertwined in complex cycles that have evolved over billions of years. The carbon cycle moves this essential element between the atmosphere, oceans, living organisms, soils, and rocks in patterns that regulate our planet's temperature and support life. Plants and certain microorganisms remove carbon dioxide from the atmosphere through photosynthesis, incorporating the carbon into their tissues. Animals consume these primary producers, using some of the carbon to build their own bodies and releasing the rest through respiration. When organisms die, some of their carbon returns quickly to the atmosphere through decomposition, while some may be buried and transformed over millions of years into coal, oil, and natural gas, fossil fuels that now power much of human civilization. The nitrogen cycle similarly moves this vital element, essential for building proteins, DNA, and other biological molecules, between the atmosphere, soil, water, and living organisms. Though nitrogen makes up about 78% of Earth's atmosphere, most organisms cannot use it directly in this gaseous form. Only certain bacteria and archaea can fix atmospheric nitrogen into biologically available forms, making these microorganisms essential links in the global ecosystem. Without them, life as we know it could not exist, as all other organisms depend directly or indirectly on their metabolic capabilities. The phosphorus cycle differs from carbon and nitrogen cycles in having no significant atmospheric component. This element, crucial for DNA, RNA, and energy transfer within cells, moves primarily between rocks, soils, water, and living organisms. Phosphorus enters ecosystems through the weathering of rocks, particularly those containing the mineral apatite. Plants absorb dissolved phosphate from soil water. Animals obtain it by consuming plants or other animals, and it returns to the soil through excretion and decomposition. Over geological time, some phosphorus washes into the oceans, eventually settling into sediments that may later be uplifted to form new phosphorus-bearing rocks, a cycle that operates over millions of years rather than the days or years of many biological cycles. Earth's water cycle, the continuous movement of water between the atmosphere, land, and oceans, connects all of the planet's systems. Driven by solar energy and gravity, this cycle transports heat, dissolves, and carries nutrients, shapes landscapes through erosion and deposition, and sustains all life. Though we often think of the water cycle in terms of rainfall and rivers, it includes many other pathways: groundwater, flowing slowly through aquifers; water vapor, moving through the atmosphere; transpiration from plant leaves; and even the slow migration of water molecules through seemingly solid rock deep within Earth's crust. The most visible manifestation of the water cycle occurs as precipitation: rain, snow, sleet, or hail falling from clouds to Earth's surface. This water, having evaporated from oceans, lakes, rivers, and land surfaces, condenses around tiny particles in the atmosphere to form droplets or ice crystals that eventually grow large enough to fall under their own weight. The pattern of precipitation across Earth's surface is remarkably uneven. From the Atacama Desert of Chile, where measurable rainfall might not occur for decades, to Mount Wailea on the Hawaiian island of Kauai, which receives an average of more than 450 inches of rain annually. Some of this precipitation infiltrates into the ground, percolating downward until it reaches the water table, the upper surface of the zone where all pore spaces in soil and rock are filled with water. This groundwater moves very slowly through aquifers, sometimes taking thousands of years to travel from where it entered the ground to where it emerges in springs or is pumped from wells. Some ancient groundwater, called fossil water, infiltrated during past climatic periods when conditions were different from today. Prehistoric rainfall now stored deep within the earth. Other precipitation flows across the land surface as runoff, eventually collecting in streams and rivers that carry it back toward the oceans. Along the way, this flowing water shapes the landscape through erosion and deposition, carrying dissolved minerals and sediments downstream. Rivers are not merely conduits for water, but dynamic systems that create their own distinctive environments, meandering across floodplains, building deltas where they meet the sea, and sometimes changing course dramatically during flood events. The Mississippi River, for example, has completely altered its path to the Gulf of Mexico several times in recent geological history, each time creating new landscapes and habitats along its course. The interface between land and sea, Earth's coastlines, represents one of the planet's most dynamic environments. Here, the relentless energy of waves gradually reshapes the shore, eroding cliffs, building and destroying beaches, and creating distinctive landforms like sea stacks, arches, and spits. Tides, caused primarily by the gravitational pull of the moon and sun, create rhythmic changes in water level that can expose vast mudflats at low tide and submerge them hours later, a twice-daily pulse to which countless organisms have adapted their feeding, breeding, and migratory behaviors. Estuaries, where rivers meet the sea, function as nature's filters and nurseries. As freshwater slows upon entering the estuary, it deposits sediments and nutrients carried from upstream, creating productive mudflats and salt marshes. The mixing of fresh and salt water creates a gradient of salinity that challenges organisms physiologically, but also provides a rich variety of habitats. Many marine fish and shellfish species depend on estuaries as nursery grounds, with juveniles developing in these protected, nutrient-rich environments before moving to the open ocean as adults. Salt marshes and mangrove forests, the dominant coastal wetlands in temperate and tropical regions, respectively, provide critical ecological services beyond serving as wildlife habitat. They act as buffers against storm surges and coastal flooding, with their dense vegetation absorbing wave energy and stabilizing shorelines. They filter pollutants from water moving through them, improving water quality in adjacent marine areas. And they sequester carbon at rates several times higher than terrestrial forests, making them important elements in regulating global climate. Earth's climate is influenced by complex interactions between the atmosphere, oceans, land surfaces, ice, and living organisms, a system with both remarkable stability and the capacity for dramatic change. Over the past 10,000 years, roughly the period of human civilization, global climate has been relatively stable, with variations of only about 1 degree Celsius in average temperature. This stability has allowed agricultural systems to develop and human settlements to expand, all within a climatic envelope that seemed predictable and reliable. Yet Earth's deeper history reveals much more dramatic climate shifts. During the last ice age, which peaked about 20,000 years ago, global temperatures were approximately 5 degrees Celsius cooler than today, with ice sheets covering much of North America and Northern Europe. Sea levels were more than 400 feet lower, exposing vast continental shelves that are now underwater. Large animals, like woolly mammoths and giant ground sloths, roamed landscapes that looked nothing like their modern counterparts. This world, so different from our own, existed in the very recent geological past, a reminder of how dramatically Earth's systems can change even without human intervention. Going back further in time, Earth has experienced even more extreme climates. During the Paleocene-Eocene thermal maximum, about 56 million years ago, global temperatures spiked by 5 to 8 degrees Celsius within a few thousand years, creating a hothouse world where palm trees grew in the Arctic and crocodile-like reptiles swam in waters near the North Pole. This warming event, likely triggered by massive releases of carbon from the seafloor or extensive volcanic activity, offers a glimpse of how Earth's climate can change through internal feedbacks, even without external forces, like changes in solar output or asteroid impacts. In the even more distant past, Earth may have experienced episodes when the entire planet was covered in ice. The snowball Earth hypothesis suggests that between 600 and 700 million years ago, glaciers reached all the way to the equator, with only small pockets of open water remaining. The planet eventually escaped from this frozen state, possibly through the accumulation of greenhouse gases from volcanic eruptions that couldn't be removed from the atmosphere through normal weathering processes because rock surfaces were covered in ice. Once warming began, it would have accelerated as ice melted, exposing dark rock and water that absorbed more solar energy. The current warming of Earth's climate differs from these past events primarily in its speed and cause. While natural climate changes typically unfold over thousands or tens of thousands of years, allowing ecosystems and species time to adapt through migration or evolution, current warming is occurring over decades, a pace too rapid for many natural systems to adjust. And unlike past climate shifts driven by natural processes like volcanic eruptions, changes in Earth's orbit, or slow shifts in continental positions, today's warming is primarily driven by human activities, particularly the release of greenhouse gases from burning fossil fuels and changing land use patterns. Earth's relationship with its moon has profoundly influenced the planet's development. The most obvious effect is the ocean tides, created primarily by the moon's gravitational pull. These daily rhythms have shaped coastal ecosystems and the evolution of organisms that inhabit them, creating environments that are alternately submerged and exposed twice each day. Many marine creatures synchronize their reproductive cycles with particular tidal patterns, releasing eggs or sperm into the water when conditions are optimal for fertilization and dispersal. Beyond the tides, the moon stabilizes Earth's axial tilt, preventing the wild wobbles that might otherwise occur. Without this stabilizing influence, Earth's axis might vary dramatically over time, causing extreme seasonal shifts that would make long-term climate patterns much less predictable. Some scientists speculate that this stability has been crucial for the development of complex life, allowing ecosystems to evolve within relatively consistent parameters rather than facing dramatic climatic swings every few thousand years. The moon itself bears witness to a violent period in Earth's early history. The leading theory for lunar formation suggests that approximately 4.5 billion years ago, a Mars-sized body collided with the young Earth, ejecting a massive amount of material into orbit that eventually coalesced to form the moon. This cataclysmic impact would have completely reshaped Earth's surface and may have played a role in determining its final size, rotation rate, and composition. The moon, in essence, represents the aftermath of one of the most dramatic events in our planet's history. Since that ancient collision, both Earth and Moon have continued to bear the marks of their cosmic environment. Impact craters on the Moon's surface have remained visible for billions of years due to the absence of weather and active geology, providing a record of asteroid and comet strikes that affected both worlds. Earth has experienced the same bombardment, but has erased most of the evidence through weathering, erosion, and the constant recycling of its crust through plate tectonics. Only relatively recent impact sites, like Arizona's Barringer Crater or the much larger Chicxulub structure in Mexico, associated with the dinosaur extinction, remain visible on our dynamic planet. As we reach the end of this gentle journey through Earth's systems, it's worth reflecting on the remarkable properties that make our planet so singular, at least within our current knowledge of the universe. Earth exists in what astronomers call the habitable zone around our Sun, the region where temperatures allow water to exist as a liquid on the planetary surface. This simple fact, combined with Earth's size, which allows it to maintain an atmosphere of the right density, created the basic conditions for life to emerge and flourish. But many other factors have contributed to Earth's habitability. Its iron core generates a magnetic field that shields the surface from harmful solar radiation. Its active plate tectonics recycle carbon and other elements, helping to regulate climate over geological timescales. Its large moon stabilizes its rotation and creates tidal environments that may have played a role in life's early evolution. In the presence of Jupiter in our solar system, with its enormous gravitational field, may have shielded Earth from more frequent comet and asteroid impacts, allowing complex life to develop without constant disruption from cosmic catastrophes. Life itself has transformed the planet in ways that have made it more conducive to continued life. The oxygen in our atmosphere, now comprising about 21% of the air we breathe, is entirely the product of photosynthetic organisms, first cyanobacteria and later plants. This oxygen not only supports complex multicellular life directly, but also created the ozone layer that protects the surface from ultraviolet radiation. Other living processes have influenced the composition of the atmosphere, the chemistry of the oceans, the formation of soils, and countless other aspects of Earth's systems. What we observe today, when we look at Earth from space or examine its components up close, is not merely a physical planet, but a complex, integrated system in which life and non-life have co-evolved for billions of years. The boundaries between biological and geological processes blur when examined closely enough. The limestone in a mountain cliff was likely formed from the shells of ancient marine organisms. The oxygen in the air is a biological product. The soils that support terrestrial ecosystems develop through interactions between physical weathering and biological activity. Earth is not merely inhabited, it has been fundamentally shaped by the life it hosts. As you drift toward sleep, perhaps floating now between wakefulness and dreams, consider that you too are part of this ancient system. The atoms in your body were formed in the hearts of stars that died billions of years before our solar system existed. The water in your cells has cycled through countless other organisms, through oceans and clouds, rivers and glaciers, in an unbroken chain since the planet's formation. The oxygen in your next breath was likely released by a photosynthetic organism, perhaps a tree in a nearby park or microscopic phytoplankton in a distant ocean. You exist within Earth's systems, not separate from them, connected to the planet's rhythms through every breath and heartbeat. Your body follows circadian cycles tied to Earth's rotation, seasonal patterns linked to its orbit around the sun, and even tidal influences related to the moon's gravitational pull. The food you eat, the water you drink, the air you breathe, all are part of cycles that have continued for billions of years and will continue long after this moment has passed. As consciousness begins to fade into the gentle embrace of sleep, remember that this journey through Earth's wonders merely scratched the surface of our remarkable planet. There are depths still unexplored, processes not fully understood, and countless mysteries awaiting discovery. Earth continues to surprise even those who have studied it for lifetimes, revealing new aspects of its complexity with each new generation of exploratory technology and scientific inquiry. Perhaps in your dreams tonight, you might travel to some distant corner of this blue sphere, to windswept mountaintops or quiet forest glades, to churning ocean depths or the serene stillness of desert nights. Wherever your sleeping mind wanders, you remain cradled within the systems of Earth, part of a planetary story that began billions of years before humans appeared and will continue long after our brief moment in the spotlight of evolution has passed. Rest now, knowing that as you sleep, Earth continues its patient turning. Tectonic plates drift imperceptibly beneath continents. Ocean currents carry warmth from equator to poles. Plants exhale oxygen while drawing carbon from the air. Countless living things, from bacteria in the soil to whales in the deep ocean, go about their existence, each playing a role in the intricate balance of our shared home. The story of Earth continues, quiet and persistent, through this night and beyond. And as the borders between conscious thought and dreams grow indistinct, let your awareness merge gently with the rhythms of the planet. Your breathing, slowing to match the steady pulse of waves against distant shores. Your heartbeat, echoing the ancient drumming of tides. Your body growing heavier as gravity, that fundamental force that shapes so much of Earth's character, draws you toward rest. Sleep now, embraced by the same forces that have cradled all life since the first microorganisms appeared in primordial seas billions of years ago. Good night.